Log on, tune in, find out. Another good idea from Cambridge.
Okay, can you all hear me? Thank you very much. First of all, I really would like to thank the organizer of the meeting and the Institute for hosting this. I think it's a great idea. I'm aware of the way the Institute works and bringing people together for all various walks of life and trying to address the problem or a problem one at a time. And it's a great way of doing this. I'm a firm believer in my own life that interdisciplinarity and banging heads together is a good way of making sparks fly. So let's see whether by the end of the week we'll have some small fire or a big fire arising from this too. I've been asked to give a little bit of an overview of some of the work I've been doing and others in this area on model-based design of experiments. I will cover a few points. Just start with some examples and see how model-based design of experiment is actually being used in anger now in various industrial aspects. I'll give you some example of industrial application of my own experience, and then draw back from there and say, in spite of patting ourselves on the back from being able to solve some really good problems, also see what are the lessons that come from that, and address some of the recent developments from our own experience in various ways, mainly to do with the formulation of the problems rather than with the solution. I believe it was Einstein who once was approached as, if you had an hour to solve a problem on which humanity depended on, what would you do? And he said, well, I spend the first 50 minutes in formulating the problem and then 10 minutes in solving it. And I think there is I'm personally quite excited about the possibilities that I've discovered quite late in terms of extending the range of traditional formulation. And I will stop in the end nonetheless to highlighting some of the reasons I believe that this technology is not in more widespread use as it should be. My own background comes as I'm a chemical engineer. I've been involved for many years in what is called process systems engineering. Is there a pointer? And what that means is that the whole business from designing new products and processes and production systems is now very much centered on the use of mathematical models at all stages. And if you can describe what's going on, then you can analyze, you can optimize all the way from the initial inception down to the supply chain and distribution and impact on the worldwide scale. So that's what we do, provide this support, mathematical support to these processes. And in fact is a very complex business because it involves dealing with processes at all kind of scales, from the conversion in the vessels and reaction and heat transfer and so on, all the way up to global impacts on value chains, but down picking up the behavior of materials within catalysts, within small assemblies, all the way up. So it's actually quite complicated, and by nature this process involves dialoguing with all kind of people who are domain experts in various areas. So as a profession we are gregarious by design, otherwise we won't be able to do our business. But I'm also a firm believer that we need all kind of inputs in order to be able to address these problems. And these days this process is helped by a very large number of support tools which are very, very powerful. Nobody would design a refinery without support of simulation tools. And more recently, I think the emphasis has been on on languages which allow the modeling of the physics in a very easy way. So if you can describe the physics, if you can describe the basic equations that regulate that, and if you can write the equations, then you should be able to use the modeling language to do that, and don't have to worry anymore about translating that into a C program with all the solutions, technologies, and in fact you can write models now quite easily. Some of you may be familiar with MATLAB, but there are many other engineering-oriented languages which do that. I've been involved with one in particular called GPROMS, which addresses that in the chemical engineering environment. And this typically also involves the use of library of pre-canned models for traditional unit operations, or whether it's separation, distillation, or reaction, and so on. And access to thermodynamics, physical property packages, which are also very, very important to describe the physics. One of the features of these languages for practical use is that hierarchical. So if you want to describe a big process as a set of Lego blocks, you can do that and describe all the interactions. And they have some very powerful solvers, powerful in historical sense, much more powerful than they used to be, never powerful enough, to allow the simulation of very large sets of partial differential equations. When I'm talking about very large sets, maybe end up with 500,000 to several 100,000 of equations, typically in dynamic, and do that not just in a forward way. We specify the parameter and initial condition can simulate, but also use data to do parameter estimation. And once you have a model, to do optimization using nonlinear and mixed integer nonlinear programming, but certainly nonlinear programming very efficiently. They also address the aspect related to the workflow in terms of understanding how engineers work in their environment in order to provide, for example, mundane but really very, very important things like management of and auditing for the evolution of models and tracking their application, so that when you want to replicate something, you know exactly what you were using at that point. So extremely important for an application point of view, although for the mathematicians involved, it may not be even of importance. And also other application integration, for example, with control systems, with computational fluid dynamics, and so on. There's some really interesting application. We can describe, for example, a whole large-scale crystallization model using detailed population dynamics in terms of how the cells, the crystal form and break and dissipate. You may have a 3,000 or 4,000 model equation in a single point to describe this, and you can then couple this with the fluid dynamic to integrate with the interaction with shear stress and other important factors. You can do this simultaneously, so that you can also use these techniques to detect the effects of geometry, and hence look at scaling up and scaling down. It's fairly recent activity, but is very interesting, and this can be done on a fairly regular basis now. So, being everything so model-centric, one of the key questions is where do this model come from, and how do I know whether they're any good, and how good do they need to be for the job on hand? These are open-ended questions, but clear that's where statistical validation comes in. If you want to do all of these things, you better know that your models are something which is good enough, okay? And enough is the operative word, because otherwise you end up with a Schrodinger's equation for everything, and that's clearly not possible. In my personal view, the ability of writing down the equation and generating the model is no longer the bottleneck. Anybody with a little understanding of the physics can do that. The question is whether those equations are right or wrong. So model validation is now a big bottleneck, and hence all the statistical paraphernalia which are necessary in order to do that. But in order to do that, you need some data, and the generation of data is in fact quite key. If you have good data, it is a lot easier to calibrate and validate a model. but very often the data are generated separately from the model, so the two things are distinct. And lo and behold, by the time you go and try to identify or validate your model, you find that the data you have are completely useless because in the different area that was a classic. I think we all been there who have been trying to do this. So the design of experiments, that's where it comes in. The idea is generating useful data that go side by side with the process of building a model. The two things not being sequential or separate, but being part of the same thing. And in fact, the bottleneck at this point is not just being able to do that, but being able to do it in an environment which supports your everyday work, rather than having to take time off, hire 2 PhDs in order to support you, and then come back 2 years later with the answer when you're no longer interested. So do this within a work environment, which puts its own constraints. I will mention this. Let me give you a couple of examples. These are examples that have been addressed recently. Very, very key within the field of addressing the energy needs. Lots of work on fuel cells. At the center of the fuel cell process is the process of essentially oxidation that goes on between the fuel and an air in a membrane cell. You have an anode and a cathode, and you have an electrolyte in between, and the transfer of ions on one end, which releases some electrons, which you can go around and light up your light bulbs. So that's the basic process. Once you start looking at the physics, it's actually quite complicated. There are the reactions themselves at the surface of the anode and the cathodes. There are electrochemical reaction, activation over potential that dictate how they happen. There is then the diffusion of all the fuel and the ions in all these systems. So there's mass transfer. All of this is dictated by the temperature and heat release, and all interactive. So actually very, very complicated to understand what's going on. On the other hand, if you cannot do that, then you cannot design. And the alternative is trial and error or do experimental work, and that's quite heavy. If you can get a model to do that, then you can say, well, what should be the target for my material design or for my assembly, for my configuration, and so on. And some things you can do with high fidelity models, and you can generate the models for this, but on the other hand, there are also a few things you cannot predict a priori ab initio, so you end up having to do a few key measurements to calibrate your model. Another example, and we come back to that again, is again in the area of energy applications. Everybody talks about the syngas economy. You can generate hydrogen from a variety of conventional and unconventional primary sources, including biomass through various gasification and so on. And once you have broken down the molecules to their essential CO and H2, then you can rebuild them in a variety of ways, including to make fuels, synthetic fuels, and so on. And Fischer-Tropsch is one of the classic methods for doing that. Very old. The Germans used to do this from coal before World War II, so it's not a new tradition. But one of the key issues there is the catalyst that makes this happen from natural gas or methane or oxygen and so on, and produces the molecules you want, assembly them for the right configuration, also assemble molecules in other configurations, so you get product distributions which are very distributed. You get a lot of unwanted, if this is stuff you want, you also get a lot of unwanted stuff, which means that the yield of your product is low and you have huge separation problems. Okay, so the economics is really dictated by what happens in these catalyst sites, and these are very big reactors. So again, you can write models for the mass and energy transfer here, but then at some point you need to identify some key parameters characterizing both the reaction and the heat transfer and how they work. And the problem is not easy. I will come back to this and show how design of experiment has been used in this area. Since you are here, you all know what this is about. And the idea is to generate this virtual virtuous circle between using your understanding of model from initial data to use the structure of this model, the information, the rich information are used within that to decide how should I plan my next experiment so that it will generate data which are useful rather than not. Okay, and this is the basic idea. There are lots of variation on this, and we'll see how some of these are applied. In a standard situation here, you will want to have a model, and I've used differential and algebraic equations as PDAEs, or they can discretize into differential algebraic equation model as the general set, and it's dynamic in general, because if you kick something and you elicit some responses in a dynamic sense, you get a lot more information. So that is a reason for having your models in the dynamic, but also because the processes you want to describe are intrinsically dynamic. You want to have those reactors are not at a particular state. You want to start and stop those reactors, so you need to describe the models in those situations. You have a design space within which you can decide how you can move, which may include both the temperature and pressure within which you can do your experiment, the ability, but also the derivatives. How fast can something react, or how frequently can you measure certain quantities, and where do you want to end up in your experiment? You don't want to end up with a very high temperature, because you need to be able to shut down and leave things at a steady state. You need to identify what are the variables you can use, measure, and the quality of those variables. You may have some choices there, variance information about the data you can going to get, and sampling limitation, which I already mentioned. And within this, you also need to design, as a part of your information, what is that you can manipulate, which is within your domain as a designer to change. And out of this, then you need to have something that helps you to decide what is the best experiment. And best means something which is related to what do you want to get out of this information. So the qualification of best is actually quite important. Typically, the objective function being used is some measure of the predicted content or value of the experiment. If you're trying to estimate your parameters within certain precision, then is related to the variance covariance or the ellipsoid of the confidence intervals. But that's quite key, because if you're trying to optimize something, you need a scalar. And again, in putting together the talk, I went back to some of the early stuff. I was one of my very first PhD students many moons ago. That helped me to formulate this as a dynamic problem as an optimal control formulation. Apparently, it has not been done, before with DAE systems. This is more or less the formulation we had at that time. 89, mid 80s. Great problems at that time. The formulation was done. Conceptually, the problem was solved. Nothing worked. We had incredible difficulty in getting 3 equations to solve, and the optimization techniques were not up there. The integration techniques got stuck and took forever, and it really we had to scale back and back and back until we could solve anything of any use. But conceptually we were there, and the formulation, including a sample time for when to do your samples over time. So there is clearly a time dimension here, but within this there could also be a space dimension. In particular, if you had discretization of partial differential equation using any discretized techniques, you end up with a large set of differential algebraic equations. The other interesting things was that for a sample system in particular, this scalar matrix we looked at, we use this information matrix, which just is the inverse of the various covariance matrix. You can call it Fisher matrix. Many names have been given it over the time. Essentially, it has two components. One is something that takes care of the dynamic sensitivity of the responses, things you can measure to the parameters, things you want to identify, at the sampling times, and the other things is something that takes care of the quality of the measurements. Okay, and you can all add them up in a variety of ways to try to transform this into a single scalar. And in fact, I think the scalar is a very powerful number because it has to tell you a lot of things about all the parameters and so on. And it's usually related to the 95% confident ellipsoid of the predicted experiment. The usual way is that small ellipsoid means high confidence, means we know exactly that the predicted experiment will give you very good data. And then this can also be translated to a single number by looking at the trace or the volume or the largest eigenvalue along this. It's quite very classical, and a lot of people then have lots of variation in how to do that. Okay, but the basic things, underlying thing, is that small ellipsoids are good. Okay, and you can then formulate this by sticking this scalar into an optimization algorithm and try to minimize the this ellipsoid and so on, and take into account some prior information experiments you've done before and initial values of the parameters and so on. This can all be done now quite routinely within software which is engineers can use as opposed to experts, and the idea is then you would use then discretize the controls and using a control interval parameterization, either piecewise constant or linear or in fact using some other higher order basis function to provide continuity, so rather than optimizing continuous inputs, you optimize a small set of parameters for your basis function with possibly junction conditions at the intervals, and you pre-select the number of intervals, and you may optimize the length of each interval and one or two variables associated with the control profiles within that. That is actually quite handy. You transform an infinite size program into a small number of optimization variables, and it's proven to be very, very useful. Typically then you can have a nested program doing the integration of your equations and manipulate the control variables on the outside in order to optimize your objective function using possibly successive quadratic programming. Has been very, very successful in this area with a highly nonlinear function. The trick here is to reduce even a very large number of states into a small number of decision variables, and for this type of problems this seems to be working very well. The objective function may contain all kind of varieties, which are varieties of information which are of interest to the to the engineers. The final values and variables, whatever your experiments, you need to leave it at decent temperature or within a safe concentrations and so on, and you can have integrals very easily. The total amount of energy you spent or the total amount of molecules you use during an experiment, because you can convert this into the equivalent differential form, and the experiment length itself can be a variable. There is also quite a nice way of handling constraints. Constraints are within this environment are quite important. There's the difference between a purely statistical black box approach, which has great difficulty in handling constraints. Yeah, you have a model, so you can predict where your states will go, and you can use that to say, well, are my constraints going to be violated or not? And you can have different type of constraints, at the end, as I already mentioned, or at given times, within the interval, or in fact at all times. Whatever you do, don't have your temperature exceed a certain maximum value, or never use more than 20% of your composition of X, because you go into the explosive range or a number of other interesting things. These interior path constraints are not easy to handle on their own, but kind of classical way is to calculate the integral of the violation and then put the integral of the violation as one of the constraints. So you don't know exactly where this is going to happen. There may be an infinite number of arcs where this may happen, but the total integral must be 0 or less than epsilon at the end. And that's a good way of translating these interior constraints into path constraints into something that can be handled. All of this has actually been packaged and is available in not in many, but in some standard simulators. So what I talk here is about a degree of practical maturity. What does mean a degree of practical maturity? It means that somebody out there is starting to use it. Okay, let's not get carried away. This is not they're not techniques that now are commonplace, but some engineers are starting to make use. And one of the reasons for that is that I think comes from the modeling side. It's become a lot easier to formulate the problems, so you don't have to spend all your time in writing your differential equation and then translate it into programs to interface with various optimization library or simulation library or so on. So that drudgery is by and large taken away from you, so people can concentrate on the use of the problem rather than problem formulation. And once you do that, then you can resort to the same powerful integration and optimization algorithms which have been done for simulation and optimization. So that's a great advantage. The other reason I think this is starting to become practical is actually rather more mundane. For example, there's a standard definition of what an experiment is in terms of inputs, outputs, things you measure, range, with forms defined to declare that. And this is making life very, very, not everybody may agree that this is a standard formulation, but here's a standard one and is sufficiently general that you can cover a variety of problems. And the same in terms of the output reports. Engineers don't like statistics, okay? And so is an acquired taste. In many cases, if you make life simple in terms of the interpretation, then they may actually understand what it is, but otherwise will not want to go anywhere near it. That's a given. So even having standardized output reports with interpretation that help to translate this fairly simple, sometimes statistical analysis into something that I can use is actually quite helpful. Let me go back. So now we can actually close this loop within an engineering environment, and let me give you a couple of applications of this, coming back to the those which I've illustrated. In terms of generating the models here, this can be done now using a fuel cell library where you have primitives for the electrolytes, primitives for the anodes and cathodes, and you can do that by selecting model and specifying the models rather than starting from scratch. And you can also resort to the thermodynamics for a lot of the thermodynamic for electrochemistry and heat phenomena. What is not possible there is usually to identify some of the key parameters. And I'll give you an example. This is a fairly standard so-called flow-through experiment we use in the industry to characterize the behavior of a single membrane. And this has a number of features. You feed air on one side and the fuel on the other side. There's electrolyte and the anode and cathode. You measure the different voltage. You measure the amperes, given from a certain resistance. And at certain condition here, with high feed-to-air flow rate, feed to air, you have a good amount of reaction going on. The conditions are fairly uniform, but it becomes quite difficult to measure the changes in composition. Okay. On the other hand, you could use a low feed to air ratio, and it becomes a lot more easier to measure precisely the changes in composition. But then you have maldistribution. It's very difficult to ensure that what happens at one end and at the other end of the membrane is the same. So there are intrinsically difficult problems, which means you have a formidable problem in data interpretation, even if you have lots of data. Okay. What happened here is, using the model of this system, we looked at what is the best alternative experiment that could be run, designing the apparatus itself, and it turned out that rather than a flow through, a recirculated flow, here will actually be far better, because the changes in compositions will be smaller, and you can measure them accurately, even with a high fuel to air ratio. And because most of the oxygen here will be depleted, and then you have little reaction even at the high fuel ratio. So this type of apparatus was designed using fairly high fidelity model of the reactor itself, and it gives a lot of very, very good data, especially when coupled with the data collected from the other experiments. So the two work hand in hand, and you are able in this way to characterize some of the reaction kinetics. The interesting things, once you do this for a single, is the lowest level component within a fuel cell. A fuel cell will have a number of additional number of stacks, one on top of the other, to increase the amount of electricity produced. The air flows in between, and the fuel in between in a sandwich form, and they are go across, so it becomes more complicated. But in fact, this can also be modeled. The flow dynamics can be modeled. You have lots of diffusions in two directions, for this situation, this can be the basic model for the electrochemistry we just described. Can be coupled with a CFD model to describe essentially the flow dynamics and flow diffusion there. And it turns out that in fact you can do some experiments without the reaction, just to identify how the flow goes. Okay, so you eliminate a big problem by looking at essentially two problems separately: the reaction itself, the flow itself, and then you put them together, and lo and behold, you find that you are able then to predict the two very important quantities here. Is the power density, which is how much electricity really it is generated and its distribution, and the temperature contours, which dictates, again, it reflects. You would like both of them to be very uniform, ideally. And then you can go back and decide about what is the optimal flow distribution and stack arrangements and so on, and ways of controlling that. Okay, so that you can do the stack. There was no design of experiments here for the ensemble, but for the individual components. And then the next situation is that you look at how the whole fuel cell will behave. In this case, this is an automotive application where you have a compressor, an expander, to deal with the dynamics of the fuel cell behavior. For example, a startup. Okay, and you have different very interesting dynamics here at startup, low pressure, and then you have a high pressure when the compressor kicks in, or when you modify the pressure in the compression ratio. And you can follow very interesting things like the fuel consumption, and you can then go back and design, and this becomes a very powerful tool. And in fact, quite a lot of the fuel cell providers, Toyotas and all that, are using now this modeling technology together with the experiment design within that to design their own version of their mobile fuel cells or for static application as well. Let me come back to the other example, which I already mentioned, this Fischer-Tropsch reaction. here we are concerned about remembering in the whole scheme of things, going from either natural gas or biomass and so on to the smallest molecules, the syngas molecules, and then from there to liquid fuels and syndiesel and methanol and DME and so on. And I already mentioned the fact that the product distribution is really the key to achieve this. And why is that a problem? That is a problem because if you wanted to do that in a very small device with no time and space distribution, you may be able to control that rather better. But if you're trying to do this in one of these humongous beasts here, 22 meters, 1,200 tons, this is a shell and tube reactor. Okay, there's lots of tubes with catalyst inside. Because it generates a lot of heat, there is heat removal on the outside. Controlling the temperature within this reactor is actually quite tricky. All tubes experience different environments, and so each of the tube has a different profile, and lo and behold, you end up with a quite a large controllable problem. Just to give you an idea, this is the Pearl development that Shell and Qatar are building in Qatar. The latest budget was $18 billion, several billion dollars over budget. Still lots of uncertainty in terms how to do that. The reason they are this way is because Shell essentially scaled up a prior reactor they had in Malaysia, just because that worked, and they didn't really want to make many changes just in case. Okay, can think about the investment here. So one of the questions is how can we understand this a lot better? And here is a scheme of this typical reactor. Say in each of these reactors you have a tube, and each tube will have lots of pellets. This is where the catalyst is. The pellets are very high surface, a lot of porosity, and really where the reaction goes on is inside those pellets. So what happens inside those pellets dictates the product distribution. And if these pellets are different here and there, or experience a different environment, or from this tube and that tube, then you'll get a very wide product distribution. Okay? The trick would then be to have all the tubes being the same and a fairly degree of constancy there. And how can you do that? Well, first you need to understand the mass transfer, which dictates how the reactants go inside the pores and they come out. And then you need to understand the interaction between the cooling and the reactions going on, so all the heat transfer problems that are associated with that. And in fact, the approach taken here was to really, rather than try to identify something as complicated as that, which is it is, and you may have 30 or 40 reactions going on here. It was to try to say, well, can we divide and conquer? And let's have a place where reactions going on their own. So a microreactor where you don't have heat transfer, and have another place which is a typical tube, and you just measure the heat transfer properties in the absence of reaction. And you can devise, and in fact, rigs were built up in the same way using this model-based design of the equipment and the experiments this way, and then you can do a certain number of experiments identifying independently the reaction and heat transfer components until you have some models of these Lego blocks, and then you put them together within the engineering configuration, take into account flows and how these interact, and again, lo and behold, you can find something which is much more predictive because you got the physics essentially right. Okay, here are some slides. Shows that the important quantities that you really want to get right are mostly obtained quite well. Okay, in particular the methane and CO2 and conversion are obtained quite well, and these are temperature and composition maps along just one pipe, and it shows that they are nowhere near being uniform, but they're a lot more uniform than otherwise they would be. So once you have confidence in the model prediction, then you can do design and optimization studies. And in fact, again, this can be done by putting together this simulation model together with the fluid dynamics that tells how the cooling fluid will be circulating on the outside. And you cannot do this for the 10,000 tubes that are in a reactor, but it takes sample some tube at the center, one near the edge, and so on. And you can look at various design ideas for getting the tubes all the same. Some of these ideas including loading each of the tube with different catalyst activity at different positions, and manipulating the geometry so you can affect the heat transfer property of the to get the same composition. I cannot give you, for confidential reasons here, the results for that particular reactor, but here is one very similar application which has been published, and these are the normalized, well, this is the yield, how much of the product you get from your reactants for a variety of tubes, and they're all the same. And the temperature profile here, again, are all the same for the various tubes, which means that you can much more easily predict the yield and optimize the yield, and also adjust the catalyst life and make life very much easier. And in fact, this is a plant that's being built in Korea as we speak. So this technology really is built on accurate values for your high fidelity models, which were obtained using the design of experiments. Now, in spite of the success of these techniques, there are some common findings that we obtain. So even if you're able to do sophisticated stuff with complex model, typically you get, in a lot of situations, confidence ellipsoids which are very highly stretched. Okay, no matter how you try, all right. And some may be good, but they maybe include lots of negative things. Physically doesn't make any sense. So correlation is actually built in, and then people start to ask, is it the model? Is it the analysis? What do I improve? Is it the data? And actually, this is very good progress, because by the time people start asking these questions, it means that they understand statistics, whether they know it or not. Okay. Do I have the right apparatus to get the data, so that my design space is not big enough, or so on? But that's the way of life. Lots of cases you cannot get away with that. And I think there is a very elementary explanation for that. Many of these phenomena are fairly complex, and very often you find, here just looking at the sensitivity profile, some parameters show good sensitivity in one state and then go to 0 or very low, and other parameters are very high sensitivity later on. This is common. In physical terms, this means that there is a change of mechanism along the road, and some mechanisms are more dominant in one area, and other mechanisms are more dominant in another area. And if you try to have an experiment where you try to do both, some of the data will have some singular parts in that, no matter where you are, and that makes it very difficult to estimate those parameters. And in fact, the way that turned out, based on intuition, those earlier cases was done is, let's decouple. Let's do some experiments for the kinetics, some experiment for the heat transfer. Let's not try to be too ambitious. But very often you have 10, 15, 20 parameters, and you don't know how to decouple. And if you started looking at it as purely mathematical problems, you find that trying to do everything together, you may not be able to do much or more than so much. So the question is, can I do this in a more automatic way? Can I identify the disjunct parameter sets and do different type of experiments? So here are some of the ideas that we've been playing with. If you start to think in those terms, well, why should I do one experiment at a time? Why can I do parallel experiments? rather than design one experiment, design two. And of course, then you have the flexibility to design two experiments which are the same, and then it give you more repeatability, essentially. Or do I design two experiments which are orthogonal to each other, and I get like two sets of values for, and you can do that. I'm not going to talk very much about parallel experiments here for the time, but there are some interesting ideas there. The other is, how do I account for the error, to start with? You wouldn't, unless you had error, you wouldn't need to do this in the first place. So every model has an error, especially at the beginning when you start with maybe some ideas what the model might be. But what happens there? And then I think I would like to touch a little bit. Are actually solving for the right? Do I got the right objectives here? And let me give you just a few hints here. I'll go very quickly. Talking about uncertainty. Okay, the classic case is that I may have some bounds, and I design experiments, and my estimate of the experiment, optimal experiment, would be like that. And when I actually do it, due to the model mismatch, I may actually violate some of the bounds. So how do I deal with this? If this violation is not big, or the violation is not important, may not be terribly life-threatening, but in some cases it is life-threatening. Here's the situation, a model from some collaboration with my colleague at Padua, Fabrizio Bezzo and Galvani, who I think have a poster here on this, looking at physiological model for diabetes. And this reasonably well understood how glucose cycle works here. There are some compartmental model for that, but this is a very non-linear response over time. If you start from the normal situation, your glucose level goes down, you die very quickly, or you have an asymmetric response and you die a little slower. This is really quite, this is in terms of hours. So it's really, constraint violation becomes important in these environments. And so one of the ideas was, how do we deal with this? There are a number of standard tests to identify individual responses. These are what the medics use to say, well, do you have diabetes, and how do you respond? And the question is, can you use a design of experiment to do better than that? I'll just give you some hints on this. There are a number of models around. You can take some of the state-of-the-art ones, and you quite quickly find that also some of them may have identifiability problems. They may have lots of parameters, but there is no way you can identify one of them. So even before you start, you have to, statistics is useful for this purpose. And then if you say what would be the the optimal placement of my samples for one of the standard tests, you can find would be in, over a time of several hours here. You want to put in some excitation, but not too much, just in case. And you can say, well, in this particular case, all the parameters will be estimated, but what is the effect of uncertainty? By definition, an optimum design will actually go to the extreme, very often to the extreme of your design space, because that's how you get more information. So it's built in that you will end up against the constraints. One of the approach to look in particular at the effect of uncertainty on the model or the parameters on the constraints was to establish the variance of the responses. So what is the probability that your responses are just the nominal one, and what's the cone of your responses? And then if you want to meet these constraints with a 95% probability or so, with 90% probability, or you want to be 90% away from that, how far back should you be? So that's the basic idea. It's actually not easy, because just establishing the variance of response for general high nonlinear system is tricky. But you can do that, and it turns out that rather than your nominal constraints here, you have something which adapts to the uncertainty that you have. Okay, and so you say, well, my new uncertainty is my new constraint is like that, and then the nominal response will be within those two constraints. Is one way of dealing with that. There are lots of other ways, and I think that's an area which will need some attention. And you can find then the 95% probability of response. Okay. The other I'd like to mention before going on too much is the one on, are we solving the right problem and what is really the objective? Now, I must say it was a bit of, with some embarrassment, I went back to some of these things because we all know that the objective for parameters measure is to minimize the 95% ellipsoidal convergence. And in fact, it is true. When you have in the limit very small intervals, now these they also have uncorrelation. They tend to be like that, but that's only true in the limit. In most practical cases, it's actually not true. So you can have a small volume there and a very elongated confidence interval, and there is no direct link with the correlation. Okay, so in general, this is actually not true. You might expect it, and so if you say, well, how do I get something that I also want from my experiment, something that produces parameters which are not correlated, in addition to being well determined? We already have all the machinery there, the variance covariance matrix, the correlation coefficients. We typically compute all these quantities just in order to compute the information matrix. So already there, but we're not using them as such. Okay, we stick all of this into a single scalar, which is the information content. And in fact, once you do that and you identify that each principal eigenvector is dominated by one parameter in this situation, then you can reformulate the problem in such a way that you get what you ideally would like. For example, you can minimize measure the correlation rather than minimize measure the information content by the ellipsoid. Or you can minimize that subject to some bound on the information content you're going to get. And you may have an initial estimate using a standard design of experiment with an E criterion. I'll give you what the basic eigenvalues will be in those situations, and you can then formulate a problem like this. Or vice versa, you can say, I can set up a problem which I maximize my information content, but with some bounds on the correlation that I get. Okay, you have to be a little bit careful here, not to put too strict bounds, because otherwise the problem may become infeasible. But you can also get some idea what these bounds might be, because if you solve the unconstrained problem, that gives you a highest value. And then you can tighten this progressively. And this correlation may be between two parameters which you specify, or maybe some kind of norm of all the values. Okay, or you can minimize the correlation something to a bound on the variance, and there's a lot of varieties of ways of reformulating the problem here, which I think eliminates by design the inherent problem that you end up with elongated ellipsoid. And in fact, you don't need to use the same objective function at all stages of your iterative design. You can start at the beginning by using one objective, maybe standard design, and then tighten up those variables which those parameters which show correlation, and you can have more tools in your palette. We have with one of my students, Franceschini, we have explored a number of ways, and this turns out to be very effective. And I must say, we're going back to solve lots of the problems where we used to have a lot of problems. You couldn't even start with the standard design because it didn't get any convergence or whatever, even from very poor situation. And here is a classic reaction example. This is a product you want, but then of course your product enters other secondary reactions as well, so it's very difficult to isolate this stuff. And as a consequence, you have a fairly high correlation between the parameters here. And I'm not sure whether you can read this, but this is the base point, and this is the optimal point. At the optimal point, you get this ellipsoid is perfectly aligned along the axis. So in order to do that, you need to give up something about your information content. That is how much and what is the trade-off. And so it turns out that in a number of iterations, you are able to get both very nicely behaved ellipsoidal convergence and also very good decoupling between the two. Okay, so it's actually quite effective. We found it in a number of situations. This is works very, very well. The real value of this, the advantage is that you can actually start to pose yourself different questions. That if I want to identify one parameter rather than the whole set of parameters, what experiment could I do, and how can I disentangle what happens with that parameter with what happens with everything else, or there are a subset of parameters. Okay, and you can really use this machinery to start to understand, can I decouple various aspects? There's still a combinatorial aspect, because if you knew a priori which parameters are decoupled, you would go for them immediately. But I think this allows you to be a bit more creative in deciding which parameters you want to do. Final word of warning. This is the approach you've been talking here is essentially variational method. You estimate how good your next experiment is going to be based on your estimate of your ellipsoidal convergence. And we are a bunch of believers. We all know they are very good. But the question is, are they really very good? And here is a simple case where, again, these ellipsoids are very good in the limit. But if you are not close to the optimum, or if you're considered a very large interval, then you find that the ellipsoids are not quite so. These are the true ellipsoid for a given confidence interval, as opposed to the estimated, but usually based on some truncation. Okay, and it turns out that these are actually not very good, even for small changes of the parameters. You go away. So what do? You have two choices. You can ask for more information, or you can ask for more reliable information. And if you want more reliable information, you can put some bounds on some measure of the curvature. Now, in order to do that, you need the second derivatives, are a little more, a lot heavier. But you can estimate, the second derivatives, and then if you can do that, you can also formulate. Let me give you my usual objective function here with some bound on the curvature. Obviously, in the unconstrained case, you don't have that, and you will get what you had before. So this is an inferior point, but inferior from this point of view, but it's better from this point of view. Okay, and a bit more reliable, although the objective function may be lower. And it turns out that you can do that. And we've just shown some initial work in this area. I think this could be automated. It's a lot more heavier numerically, but it's just a warning. Okay, I will very quickly close. There's a number of other developments I think are quite interesting. The idea of both using a measure of uncertainties and continuous measurement. I think one of my colleagues, Fabrizio, will cover tomorrow in his presentation. Cover some, so I don't. And I didn't cover going to parallel experiments. There are also some interesting ideas of combining model discrimination and parameter estimation, which I'm going to. Conclusions. I think I haven't even talked about the maths or the solution techniques. I've said they're good enough. There's room for a lot of improvement, but we are starting now to see some serious use of these, not just from aficionados like myself or a few colleagues which I see here in the audience who are the true believers, but the unbelievers, those who are really skeptical about it, okay, and using it in earnest in very good industrial application. And I think the key for that is to hide all of this, behind some general purpose software. I believe we're now getting to to a much better understanding of what is best design and how we can incorporate it into the formulations. The dynamic optimization framework that I've described, and most people are using, in fact, is very good for that, because you have multiple objectives, and you can choose one objective function, and everything else becomes a constraint, or you can have Pareto solutions, and there are a good way of doing that. The thing which is more exciting for me at this junction is the ability to formulate and be much more creative in the formulation of the problem. There's still a lot of issue to do with the mathematics, multiple shooting, and global optimization versus local optimization. I think are two of the key issues here. And really to really conclude, some comments on what is I believe the barrier here. I already mentioned engineers don't analyze statistics. Let's not even mention chemists or biologists. It doesn't come natural. It's an acquired taste. So I think the only solution I can think of, you really must hide it inside the box. Everybody drives their car. They have no idea how their engine is being optimized 250 times a second today, but they're very happy to do that. Okay. This really puts a lot of difficulty on the ease of use and the robustness of solution. Let me point out on the last bit. If you have 90% success in many of your algorithms, you'll probably be very happy. Okay? But if you had your car breaking down once every 3 months, you think this is really a bad piece of engineering. I would not want to go anywhere near it. And so 90% success rate means that some people who are trying to use the technique will spend 95% of the time solving those remaining 10% of the problems for the first month, and then they will give up, and you're back. So I think there is a very big challenge here in getting from to the 99% success ratio, and that's a big challenge for the numerics, for the algorithm designers, for the people who say, well, you need to simply advise on what's going on and why things are going wrong. The other thing which I think is we are our own worst enemies. Every time we have a little variation of a method, we give it a different name, creating a total confusion outside of this community, sometimes even inside, in terms of who is doing what and for what purpose. So I think a little bit of attention to branding. Other communities have done it far more successful than we are, and I think we maybe can pay a little bit of attention there. Thank you very much.
Although I hope we'll have much time for informal discussions, now we have some formal discussion. So if you have some questions, please, Henry.
So it's a very nice talk, so I'm not going to be critical, but I slightly disagree with the idea that somehow statisticians should hide deep down inside some box. And this won't appeal. This won't appeal. I'm a statistician who works with engineers. So, yes. In many fields, in compartmental modeling, in epidemiology, in environmental methods, including differential equations, there's a big move now in statistics, work by Ramsey and others, and papers in the Royal Statistical Society, in which the differential equations and the statistics get together very closely. So I sort of disagree with the idea that, what we're here to do is to actually bring the subjects closer together. I'm going to learn some thermodynamics. So, engineers should go halfway to learning statistics. I have one technical point. In addition to that, is that when you do your maximum likelihood estimator with small sample size, if you bias correct, you get a much better coverage than if you don't. So statisticians can contribute.
I agree with both your points. The point about hiding inside the box was not a matter of making it invisible; it's making it accessible. And I think accessibility has been an issue here. It's almost out of desperation that I said make it accessible, because the other solution would be training and understanding. And I wouldn't say I almost given up. Being in a university is my job, but I can see that is translating complex statistical issue in sets that make sense. I think this is the key. It is the interpretation of the statistical test, and it really takes a lot of skill to be able to do this, not just on a case-by-case basis, but incorporate it into something that does it for you on a reliable basis over a spectrum of problems. The interpretation is much more difficult than churning out some statistical numbers. Yeah? So I really don't disagree with you.
I had a question on the correlation of the parameters. Why is it exactly bad? I didn't understand. I didn't understand why the correlation of the parameters.
Why is correlation bad?
Yes.
Because I have two parameters and they're highly correlated. I move one and the other goes down. I move the second one, the other goes up. I cannot really identify them together. And very often means that I cannot identify, maybe an issue with the model has too many parameters. But you want to know, is that because my data are inadequate to identify these as independent parameters, or because they're generally independent? They're generally related. And so correlation is bad because it means low confidence in your parameters. Okay? Does that answer the question?
Well, you have errors in the data that translate through the model to a variance-covariance matrix of the parameters. So well, this is first approximation. So if you have a small confidence region, but which is not aligned to the axis, you have a good estimate of both parameters. So you'll be okay. At least that's what
That's what I also believed for a long time. But in practice, this actually does not happen unless your confidence intervals are small enough that you're really close to being in the limit of the optimum. Very often you have fairly elongated confidence interval. You cannot really get away from your correlation. And the reason is that because you don't ask about correlation as a part of the problem formulation. You think it's implied. My observation is that it's not. So if you ask for it, then you have a good chance of getting it. There's not a big extra step. All the information already somewhere there. Just need to add another constraints and so on. Thank you very much.
Thank you, Sandro.